Well, firstly, an apology. I did try to negotiate an early start for dinner, for lunch. You guys lost out, I'm afraid, so we're going to be the extra. I was going to get to sort of, 12:50 and say, right, it's lunchtime, and that's a nice quick start. So we're going to sadly be going on till 1 o'clock, and so please think up some good questions. Replying or responding to the, I've done so many things, that's because I'm so old. When you're twice the age of everyone else, you do twice as many things. So that's you just got to fit it all in. There's not a huge amount of code in here, I'm afraid. I could show you loads and loads of code, but it won't mean much. You've got to understand the basics of what you're trying to do here, and that's what I'm going to try and show you. There's a lot of talk in these slides about getting the images, how we process the images, not getting them from James Webb Space Telescope, but just understanding the physics behind the images. And everything I do in my back garden in London is exactly the same, and the files are exactly the same. So after spending, as COVID hit 2019, Amex was kind enough to double the amount of money you got on your Amex points, just to try and encourage people to make them feel better in COVID, and that left me enough money to go and buy a telescope. So I bought myself a nice one. And while we're all sitting at home, unable to go out or anything, you can get into the back garden and you can do a bit of work. So that's where I sort of kicked off this astrophotography. My background is from university is astronomy. So it's always been a hobby of mine, and it's something that I've spent a long time doing. But to me, astronomy was always something you needed to go to a mountain in Spain or in Argentina or somewhere to get these incredible images. And I was absolutely shocked by what you can do today, and I hope you will be too. And these are things that no matter where you live, whether you're in downtown Tokyo, downtown London, New York, or one of these bright places, or basically anywhere else. In fact, London's probably the worst because of the clouds. You can do some pretty amazing things. And to my delight, when I went onto the NASA sites, absolutely everything from the Hubble Space Telescope to all the various other telescopes out there and the James Webb Space Telescope, you can download this data, and it is precisely the same data as I get in my back garden. So it's literally just putting it on and processing it. So the whole background, which is what I'm going to give you a little sort of insight on here, is enough that you need to basically get into the processing. So as I said, my passion in the early days was astrophysics. Why didn't I go into it? Well, I did astrophysics in London at UCL, and literally everyone went straight into finance after that. So I've been in finance since the mid-80s, and in IT as an assembler programmer, or hardware originally, assembler, C++, with the sort of Objective-C, C++ wars in the, mid-late 80s, with your famous Danish person, Bjørn Strustrup, who I met, and then into Java. Very lucky to get into Java in the very early days in '95, and now I have to dabble in a lot of different languages, and one of the best things to do that with now is ChatGPT, because you can basically take any bit of code, paste it into ChatGPT, and say, translate this into whatever you want. So anyone out there that is fearful of getting into different languages, that's my tip. ChatGPT, paste, cut, paste, and it works. One of the other things I enjoy, as anyone who's been on any of these things, is the odd little drink. Denmark is a superb place, not perhaps for wine, but certainly for beer. And when we were at university in London, our observatories were in the north of London, and it was on cocktail night, which meant it was a very difficult decision to make between staying at cocktail night or getting on a tube and a bus, several buses, to get to this observatory to draw a picture of the moon upside down, because basically, if it was ever clear, which was like once a year, all of the third years and postgrads would get access to the telescopes. So it was a very quick decision that cocktail night was definitely where we stayed. One of the things we can now do, this little box here, the red box, is actually this thing here. The entirety of what you need is put into this. This is basically a Raspberry Pi. It's got a bunch of connectors on it, and we literally use this, the aerial here, we connect into with a mobile phone, and it now means most of my astronomy once I've set the telescope up, I can actually sit in the lounge, watch Netflix, and over a glass of wine. So it does make astronomy very easy, quite delightful. These two telescopes are the two that I use. The two on the left and right are in fact the same telescope, but it's a rather special configuration. I can put the camera on the front, which gives me a much wider field of view, or I can put the camera on the back. The light then bounces up an extra trip, and I put the camera on the back, and it gives me a very detailed, long telephoto view. So a 2.3 meter telescope in terms of focal length. If you think of cameras, your average telephoto is 200, 300 millimeters. This is quite a long telephoto lens. And the one in the middle is the sort of portable one. It's the one I can basically, if it's slightly cloudy and I'm not sure whether to set everything up, I can basically pick this thing up, take it outside, and everything's ready. This is my main challenge. Well, one of my main challenge is clouds. What if you believe in God? It's God's natural filter. This is this big obscurity filter that goes across everything. Both of these maps on the bottom are to scale. It's one big thing here. I live about here, right in this bright bit in Ealing, in between Heathrow and London, and it is. I mean, you could literally read a newspaper outside if it's cloudy, because the light just reflects back off the clouds. I'm lucky if I can pick out the main constellations at night from my garden, and which is why I always believed that there was very little point in doing any astronomy in London if I go driving somewhere. As you can see, these two are to scale, so you're very lucky if you live here in Copenhagen. If Copenhagen's here, obviously Malmö, Helsingborg up here, this is the main island. You can go for a short drive and you're out into pretty dark skies here, which is great. As you can see in London, to the same scale, I've got no hope. I need to drive for hours and hours to get to somewhere dark. And as you can see that with the rest of Europe, it's a pretty sad state of affairs. This, however, is one of the earliest images that I took. This is with an ordinary camera, so you don't need specialist cameras to do this. This is also without a complex tripod. The tripods we use have to track and reverse the Earth's spin as we go around. This was actually lots of very short frame photographs, which I then stacked afterwards. So if you think 1 second, 1 second, 1 second, but you do that for hours and you basically stack these afterwards. So the secret to this is a filter, and we'll get into those very shortly. This is the Heart Nebula. No guessing, no clues as to which one that is. And the other one is the Soul. So it's the Heart and Soul Nebula. In terms of size, the Moon would very easily fit inside this frame. So these are pretty big. The Moon is about the same size as the Heart Nebula there. So that gives you an idea. These things are out there. They are absolutely enormous in the sky, but you just can't see them with your eyes. So a little bit of background on, we'll talk about the cameras, we'll talk about the way the cameras work, we'll talk about light, the way light works, and then look at some of the computational side of that, and that's where I've got into I've done quite a bit of Java off the back of that to do some of the computation, and we'll talk about that. So the cameras you have in your phones, every single one of your phones that has a camera, every single one of your cameras, I think there's only about 1 or 2 exceptions made by specialists, like Leica, for example, they're color cameras. But a color camera isn't naturally a color camera. It's actually a black and white camera. So at the bottom, you've got these CMOS pixels that will pick up very efficiently light with an efficiency of typically 70, 80, and sometimes 90%. So for 100 photons that hit it, you'll get 80, 90 electrons that come out of these cameras. They're very efficient. And that's exactly what we need in astrophotography, as I'll get onto shortly. The problem with color cameras, as you can see from here, the vast majority of the light, i.e. 60-ish, 70% of it, is stopped. So for the red filter, the green and blue are stopped. For the green filter, the blue and red are stopped, etc. So we're only actually getting 1/3 of the light into these filters. This is a Bayer filter, and this is what you have in your camera. Not only that, but to get the true color of the light, you need to put 4 of these together. And so in fact, you've only got 1/4 of the resolution. What your cameras do now, some of the new iPhones, some of the more modern phones, and I guess Android does that as well, you can sort of guess if you've got a little bit of light on one of these pixels, but you get the color from here, you get the resolution from an individual pixel out of this. And that's what they're trying to do. But for astrophotography, this is really not great because we're looking for pixels in the tens, and to lose 2/3 of those pixels is really not a good idea. So a color camera is what you start with, but it's not, if you're getting serious, is what you want to carry on with. The spectrum that we see, and for anyone that's interested, over lunch or later at the bar, this is a spectrometer. All it is a diffraction grating. You can look through this at any light source, any one of these around here, particularly your computer screen, and you'll see this spectrum. And if you look at the sun through this, you can actually look at close to the sun with it. On the sun, you'll see these little lines that go across. If you look at these lights, I'm not sure what they are, whether they're tungsten or LED, you'll see bright bands, and that's basically how the light's made up. So the sun that we see is basically the spectrum. So if you take this as the spectrum across, the strength is basically up here. The peak is, I'm referencing this, not the graph at the top. The peak is around green, and then it comes down and goes off for a long tail down into the infrared. And that's the black body radiation. There is plenty of green lights in the sun, and that's why green is, hence this laser here. This is this is about the same power as a red laser, but because your eyes see it more sensitively as green, it appears to be brighter than the red lights. So if you want something bright, you tend to look in the green spectrum on this. However, space, although the stars emit this broad spectrum, a lot of the other stuff in space doesn't. And the things that we want to take pictures of, those nebulae that you saw earlier, are actually emitting light in very specific spectrums, just like if you've got a fluorescent light, for example. It's basically emitting one wavelength inside, which is then fluorescing in a different wavelength. And in space, there's this, pretty much 99% of it is hydrogen. And we have this hydrogen alpha. This is the primary emission in space, and it's red. And so if you point your camera, or if you were to be able to see into space with enough detail and resolution, you will see a lot of red around, and it basically emits in this red spectrum. We have sulfur here, which is very close. It's a slightly deeper red. And we have oxygen, this is the third emission line of oxygen in green. Now there's obviously oxygen 1, oxygen 2, and there's hydrogen alpha, hydrogen beta. They all fall in different places. But these are the primary ones that we use. And what we do is we look for a filter here. And what this allows us to do is basically everything to the left of this and everything to the right of this particular filter is taken out. And that includes all the light pollution. So if you've got street lights or bits of the moon bouncing off anything or anything out there at all, we're basically stripping that off. And this allows us to basically photograph a very, very narrow band of wavelength. And these bands from here to here is about 350 nanometers in spread. And these are typically 3 or 4 nanometers in wavelength. These filters, sadly, and here is one of them, this is a dual narrowband, so this lets two of those wavelengths through. So this is what you'd use for a color camera. We use single narrowband wavelengths for monochrome cameras. So again, if you look at any one of these lights through this, you'll just see these 2 narrow bands. When you look through this and with your eye, you think you can see color, but you can only actually see these 2 things. The brain's very clever at making up these different colors. These are sadly incredibly expensive. So one of the most expensive parts of astrophotography, you've got your telescope, you've got your camera, you can use your ordinary camera, you can use a relatively decent, any telescope. But if you really want to do stuff in a large city, you need one of these. You don't need these quite so much unless you're getting into specialist stuff or living out in the middle of nowhere. When we're looking for light, this is M27, the Messier 27. It's a nebula which emits, as you can see, different wavelengths. So each of these colors here, this will be bits of oxygen, and these will be bits of hydrogen. And as I'll get into shortly, we can recolor these because that's just what we do. It just makes it look prettier. And that's the artistic side of it. But these stars here, which actually in this, because it's cinema, it's quite good here. In previous ones, you can't. So these stars here are about magnitude 15, maybe. These might be 10 or 11. This might be 8 or 9. Magnitude scale is basically the sun is minus 26. Sirius, which you can see, the brightest star in the sky, is about -1. Vega is the sort of definition of 0. It's one of the closest stars. And you can see up to about magnitude 6 with your naked eye. So none of these you would see at all with your naked eye. You might just see this one with a pair of binoculars. But these stars here, you can see some of these tiny ones, we're getting about, with literally a few hundred photons per square meter. Square meter is pretty big. That's a few hundred photons per second. So when you put these through a telescope that size, we're talking about tens of photons per minute. And your camera will it'll basically measure it from 0 to typically 65,000. A lot of the cameras may be 0 to 10,000. And so if you're only getting 10, 20, 30 photons on these, they're very, very faint. These, however, are also faint, but they're actually quite bright. The Orion Nebula is so bright you can see it with the naked eye. You can't see the beautiful splurge that it is, but with a reasonably good pair of binoculars or a telescope, you can see the wonders of the Orion Nebula, and I've got a photo of this right at the end on the Orion Nebula. But what we do with these filters is we block out all of this, and this comes through just without any hindrance whatsoever. So we're basically making the rest disappear and bringing these out. So into now, this is where I've got into it from a programmatic point of view. What I've done, I tend to model this. So what I'm trying to do here is I'm trying to understand why my telescope is making certain stars larger, smaller. Well, I know why that is, but I'm trying to model it in a way that I can, so basically making something blurred is called convolution. And if anything goes through a small hole, a small aperture, the diffraction basically spreads the light out, and that basically makes it out of focus. If anyone, just quick show of hands, people who are into photography? Okay, it's quite a few of you. So you'll know if you've got a very wide aperture, you'll get a very narrow depth of field. That's a different thing from diffraction. On an average 35 millimeter camera, if you go past about f11, f16, you'll end up with more diffraction than you will from the quality of the lens. So the lens is fine, but the physics of getting the light through that very tiny hole means that you actually get what's called a circle of confusion, diffraction blurredness. And this is what this is. That's every single star that we see, unless you're actually in space for just the nearest stars, is a single point source of light. So that should light up 1 pixel here. It should be just 1 pixel. But because it's diffracted, it creates a cone. And you can see this cone here. It's actually obviously 3-dimensional. This is Excel, believe it or not. I do like Excel. It's about the only good thing from Microsoft. They could do a lot better with it. Apparently now it's got Python in it, which is great, except it doesn't work on a Mac. And it's now got some AI in it, as I heard this week as well, which is great. But I do love Excel because it's a great tool for modeling. And so I use this a lot for modeling. So you can see a lot of my calculations here. You've got the speed of light. You've got Planck's constant. I'm working out the brightness of the various different stars. I'm working out the light that comes from them. Now, these formulae here are basically, it's basically the Gaussian error function to try and work out how much light is falling on each one of these pixels. So what I've done is paste these formulae here into each one of these squares going across here to basically work out how many pixels across you are from the center here, so that you can see these offsets here in micrometers. And this effectively works out the amount of starlight that falls in each pixel. And so I've modeled this in Excel. I built a test case, which goes right across here, from data from NASA. So I know how this works. And basically, so those are my test cases. Somebody asked earlier, did I build a test case? Yes, I did. So I built all these out. I then test them down here. These are just cut and paste, so I'm remembering what's happening. This is my visual side of it. It's all in Excel. And again, the little graph here as well, all in Excel, is obviously. And then I commit this to code. So I start to code this. My goal here is, as this is a single point source of light, and it has been convoluted or diffracted, that's basically the physics, quantum mechanics of light, you can effectively apply this becomes a Gaussian function, you can apply this in reverse, and it's what's called deconvolution. And if you apply that in reverse, you can unfocus images. You've seen those movies where they see a number plate from taken with a mobile camera, and all of a sudden you can see the guy driving it and what's on his mobile phone. Not quite that good, sadly, but it is absolutely astounding what you can do by undoing this convolution here and reapplying this back. And once you've worked out this or convolution grid and then work out the inverse matrix of that and apply the deconvolution, you can actually get some incredible resolution out of this. So this, I'm not used to this. It's great having a huge screen here. So just to give you some of the idea, again, this is plotted in JavaFX, which I absolutely love, but it's such a pain in the ass now that Java's it's sort of out of Java. So this is a bright star on a Bayer filter, so basically in color. And what's happened here is it's gone up and it's clipped. It's because there's too many photons. I'm sure you've all taken a photo of something and the sky's just gone white. You go, hang on, there were some nice clouds in the sky, I can't see anything. Well, it's basically because you've hit the end of the 65,000 pixels and it clips. And this is like almost every star that you see, it clips. If you can see the star, you've clipped it. And so if you want to get colors out of stars when you're taking astrophotography, you've got to be very careful and make sure you don't clip. Now this is a black and white, so the yellow here is basically my indication that it's clipped. This also is clipped, but if you wanted to take this in a Bayer filter, you've actually got to do very short exposures to make sure you get a nice graph like this, and we spread the color out. This one here, behind me, this is what happens when you've got a very faint star or you've got a lot of background noise. So this is light pollution here, and as you can see, this creates random noise at the bottom. Again, all these are plotted based on these functions here. So modeled here, put into Java, displayed on JavaFX. This is the star, what it looks like. When I run this, it actually runs in real time, so you can just sort of see the background going. So it's to sort of show me what the ideal perfect case is for the star, so that I know what I'm measuring against. I'm not going to show you the code because there's a lot of matrices, and matrices in Java don't really work. If you create classes for them, it's all very nice. You can see how it works in the classes, but classes are an incredibly inefficient way of working. So basically, I've put everything into long streams of binary, basically, and I treat them in binary. So there's a lot of, I'm treating Java as if it was C. And that's only the way you can get performance out of these, because you're working on a sort of a 12,000 by 8,000 image, and you've got to do that sort of processing at quite a lot of complexity. So quickly onto stacking. If you were to take a 1 hour exposure, this, by the way, is the Orion Nebula. There's one here, there's another star down here, and another one here. That's basically the sword of Orion. Now up here, we get 1, 2, 3. Those would be the belt of Orion. And obviously the others are much higher. But you can see this with the naked eye. That looks like a star because that's all you see. If you get a pair of binoculars, you'll see a fuzziness around here. You won't see those colors with your eye because your eye isn't sensitive enough to pick up these colors. But even with the most basic camera, in fact, even with a mobile phone, today's mobile phones, and even the most basic telescope, you will see this with a mobile phone. It's actually quite stunning. It is the brightest nebula in the sky, and it's just coming up now. So if you're out there, give it a go. It's bright enough you can do handheld with this. But anyway, what happens, particularly as I live very close to Heathrow, but in the dawn and in the dusk, because the sun is only just below the horizon, it's lighting up the satellites as they go across. And so this is very typically what you see, and thanks to Elon Musk, you now get the little trains that go across. Quite pretty to see, but quite annoying if you're trying to take photos of something. So what we do is we take lots of individual images and we stack these together. Now there's another complexity added to this, is every time you take an image, you have what's called read noise. And read noise is random noise which goes on top of the image. So if you take too many short images, you end up with a lot more noise. If you take a long image, you end up with less noise, but you end up with a lot of these things. And also, squirrel on the telescope, or one of my kids walking past it or something, and the telescope moves, and one slight movement, and all of a sudden everything's lost. So it's a compromise between the shortness and the length that we do with these. So typically, I'm doing about 5-minute exposures. Now, processing these or stacking them takes a huge amount of processing power. This is an M2, and as I moved up from the i9, Intel i9 that I had, this is now about 5 times faster than my Intel. But to process a typical evening's images, you're looking, certainly on the Intel machine, at about an hour and a half, 2 hours of processing. And the Intel one would basically burn a hole through the desk while trying to take off. These things are much better. It'll do it in about 15, 20 minutes. But this is my the CPU. And you think, okay, this is bad, and then it gets worse. And it just goes on. And of course, it's paging out, so it's going onto the swap space, etc. And this is one of those things where you've got all the images, you have to clean them up, you take out the satellites, you do all these things, and you basically put everything in, you click a button, and you know your machine is utterly useless. I mean, if you go to press the, oops, I did something wrong, cancel, you could take 10 minutes before it's even acknowledged the fact that you've moved the mouse. This is a lot of computing power. But you get everything ready, you get it all set up, you press go, and you go away, you have dinner, you come back, and that's the really exciting part. This is the Crescent Nebula. It's up almost straight above us just after it gets dark. This is a single shot, 5 minutes, in hydrogen alpha. So remember, hydrogen alpha is the really bright one. This is in the red spectrum. As you can see, this will become relevant to this Hubble the James Webb Space Telescope, because this is the data that we're trying to get out. So you can see this is the nebula here. All this is basically hydrogen nebulae, which is pretty much all over the place, but there's quite a lot of it around the Milky Way. Now, as we process this is an hour now. As you can see, we've got a lot more definition. We're getting a better signal-to-noise ratio. What we now do is basically take out the stars. To take out the stars, this is not putting it into Photoshop and just clicking little things on the stars. This uses AI. And there's quite a lot of AI out there, and this is brand new. This is the first ones came out about 4 to 5 years ago, a thing called StarNet, and then there was StarNet++. And now there's a guy called Russell Crone, I think his name is, who has a thing called Star Exterminator, and this is completely AI. And he has trained this on the NASA images. So he's downloaded all the NASA images, and he takes a section of the sky, and he says, he's manually taking them out. He says, this is what I want, this is what I've got, and I want to split the stars from the nebulae, and he trains this. It takes weeks and weeks on a very large computer to do it. He then publishes these libraries. You can run these, and it basically it splits the stars from the nebula. The advantage of doing that is you can process both independently, and so you don't upset your stars as you're processing the nebula. Now, that's hydrogen alpha. We now do oxygen, sulfur, and we'll keep as well. Now, watch this little area here. So we've got a little area here. The sulfur, there's not a huge amount of data in sulfur. So sulfur is always that, shall I bother with the sulfur? Because this might take 3 hours. This is another 3 hours, this is another 3 hours. 9 hours is basically the entirety of my winter's viewing in London, because it's cloudy. So 9 hours is an unbelievably good night, and it's either set, it's cloudy, or something's happened. So 9 hours, you might think, okay, I'll guess I've got 6. So I'll do 3 on here, I'll do 3 on here, and I'll not bother with this one. So certain areas have different things. But anyway, watch this, because that's what I want to point out how this works. So as we process these, we can assign any one of those what we call them SHO, sulfur, hydrogen, and oxygen, to any of the 3 colors of RGB, which are the colors that we see or we use on our laptops, TV screens, and things. And as we assign these differently, you'll see different features. Now, you can't see the sulfur in here at all. Whereas this one, I've applied it in a different way, and you can see the features of the sulfur coming out here. Now, this sticks out nicely in both, but you can see it sticks out more prominently here because it's colored differently. And this is what's important with the James Webb Space Telescope, because it's not just taking these 3 filters, it's taking about 15 different wavelengths. And what's important is you can take those 15 different wavelengths. You've only got 3 colors you can play with our human eyes, or that we can play with the average monitor. And the secret is now to take the combinations of those 15 and apply them in interesting ways that you can start to see features like this. Now, you would miss that in here. You wouldn't see it at all. There's nothing there. And that's the secret. And this is what amateur photographers are doing. So just quickly have a quick look at those 2. And these were taken from my back garden last year, I think. There's plenty of resolution there. It's 12,000 by 8,000. We do a thing called dithering. Dithering is where every shot we take, we move the camera very slightly. The reason for that, as I explained, each star is basically a splodge, and it goes over multiple pixels. If we move let me put that down. So if this is your image frame, and you've got a point source here, but you've got a splodge on it, if we move this around, we can actually work out where the center is. And so by processing multiple ones, all having moved around, we can actually see, and we can basically get more information out of the image. This was discovered, this was invented by the people who work on the Hubble Space Telescope. And they do this with Hubble now. They move it around very slightly so you get a better resolution. Similar to if you've looked through netting in a hotel, or if you have it at home, you can't see through it, but if you move your head around, you can actually you can see what's behind it. So it's the same effect. On to infrared. Infrared, we don't see with our eyes, and our eyes make up, everyone sees things differently. I dare say you've all come across this image when it's hit social media a few years ago. It's basically, people see it in different ways. I can't even remember what it was, whether it was gold and white or blue, whether these are blue. And your eyes, everyone's eyes see very, very slightly differently in the colors. But once we get outside of our visual spectrum, we're left with this. Now, I took this because I just happened to walk around with infrared cameras, as I'm sure most geeks do, amongst other things. This was in Colorado, and this guy lives in Florida, and he doesn't have a coat. It was about minus 10. These 2 guys come from Northern England. They have coats. So, as you can see, he's about the same sort of physique as myself, but I actually had a coat as well. I was, because I come from England. But you can see the differences in colors, and this represents the infrared. So here, the white, it's basically, we've applied a spectrum to this infrared. And this is what we're doing. This isn't visual. You can't possibly see this with your eyes. You can only take the infrared and you can apply color palettes to it in order to see it. And that's what we're doing with the James Webb Space Telescope. This is the Hubble. And what's happening here, this is the 3 colors that I spoke about, or the 3 wavelengths I spoke about before. This is sulfur, hydrogen and oxygen, and we've applied these to a color palette, and this gives a nebula which is predominantly red if you just take an ordinary visual photograph of it. But as you can see, it gives you this is what's called the Hubble Space palette, and it gives these beautiful transitions from the red through orange, yellow, green, etc. into this. And again, some stunning images. That isn't actually the Hubble Space Telescope. Again, I took these from the back garden. So this is from my back garden. So why do we go into space, or why do we have to go into space? Well, this is the transmission that we get here on Earth. Very fortunately, this bit is, the ultraviolet is shielded by the atmosphere. And that's good, because we wouldn't all be, virtually none of us would be here, we'd all be fried to bits with cancer and various other nasty things, because all of this stuff here is what gives you sunburn and irradiates you. Now, if we lose the ozone layer, this curve starts to come down here, and we all get fried. So that's not good. This is the rest of the atmosphere. Some of these peaks here are things like water vapor, and this absorbs the infrared. Now, the James Webb Space Telescope photographs in this range here, in the infrared range. And as you can see, you can't see this from the Earth. It's basically absorbed. Just the same as if we have ultraviolet, and there are satellites up there doing ultraviolet, they have to go into space to be able to do this. And the reason our eyes have adapted to the light that we got, there's plenty of light. So remember, the spectrum from the sun is roughly sort of like this. It's black body radiation and comes down into here. We feel the warmth from the sun in the infrared down here, but our eyes have adapted to this little slot here. They could have adapted to this, and there were probably some animals that can see in this area here, but our eyes have adapted to this little range here. These are the filters. This isn't a photograph of my filters here, but this is very similar. We put them in a filter wheel, so it just revolves around. We have luminous, which is basically the whole visible spectrum, cuts out the infrared and ultraviolet. We've got a red, green, blue, sulfur, hydrogen alpha, and oxygen 3. And we basically take half an hour in each one, move it around, and do them. This is the James Webb Space Telescope. Now, you imagine how much these cost. Each one of these is about 300–400 euros. Not the red, these red, green, blue, they're cheap. They're nice. They're like sort of 50 euros, but the other ones aren't. And imagine these. Now, these are probably in the range of several 100,000 each. And they probably had to make 2 of them just in case one of them broke, or 3, or multiples of these. So you are looking at a piece of equipment that I have no doubt I would put a lot of money on that, costing well over 10 million, probably closer to 50 million, just for this. This is the most important part, that and the cameras of the James Webb Space Telescope. So this filter wheel revolves around, and each one of these are the wavelengths. So these are, you've got a lens up here as well. So these are the wavelengths in nanometers, W for wide. I can't remember what the others refer to, but basically these are the filters. These, if you go to the NASA site, these are effectively what the filters cover. So we have some narrowband ones here. These cover very specifically and quite importantly things like methane, because if you're looking for potential life on other planets, you've got the starlight, which remember is a broad spectrum of light, with a couple of bands missing from it, but basically a broad spectrum of light shining through a planet, through the atmosphere of a planet. And in that atmosphere are molecules of potentially organic molecules, or molecules produced by organic material. And some of these shine, if shine is probably an exaggeration, but some of these pop out in these wavelengths. I don't know what these specific ones are, but there'll be things like carbon monoxide, methane, things like that. So this is what they're designed to do. They're designed to look for signatures of life on other planets. And that's one of the many roles. These are more broad spectrum, and you can also do these and subtract these. So you also get quite a lot of, there's some clever stuff you can do with subtracting filters as well as adding them. But when the James Webb Space Telescope takes a picture of something, it takes a picture and it uses all of these, pretty much all of these, not all the time, but it produces all of these. So what you can do is you can download this data, and I've got the web page if anyone wants to take a quick snapshot of it. I'll put the QR code so you can go straight to it on there. It takes all of these pictures and you can download them. Now, just as I did with the picture of my colleagues in Colorado, you can assign colors to those, just as NASA have done. But if you assign those different colors, you can get more data out of it. And what amateurs and hobbyists are doing is doing exactly that, because look how many filters there are. There's a good 15 or so filters here into 3 colors. People are finding different things, and we're literally seeing amateurs pick data out of this. So anyone that's interested in going to this is, there's a pretty mind-blowing amount of data on this. You can download all of these images in exactly the same format that I get out of my cameras in my back garden. And there's a filter at the top, as you can see as you go through this. It is quite unwielding, because you've got to pick the dates you want, you've got to pick the target you want, you've got to know a little bit about it. And so if you're looking for a particular thing, do a bit of research first to work out what the name of it is, what the scientific name is, when it was taken, and that will reduce your list. Otherwise, you'll get a list which is literally thousands of items long, and you've got to filter through looking for the bits that you want. So if you do that, it's quite mind-blowing in size. Now, this is some of the data that I've downloaded. It's one of the earlier images. It's the cosmic cliffs. It's not visible, sadly, from the northern hemisphere. It's in the southern hemisphere in the Carina Nebula. And I've downloaded 3 different in fact, I downloaded about 10 different wavelengths, and I picked these 3. And you can see very different things in here. You can see, for example, this looks like mist, but of course this is from one wavelength. You see different wavelengths down here. You'll see stars here which don't appear in here. So these 2 do. And you'll see others here which, you'll see brighter stars here, which are dim here. These are all different stars and different wavelengths that you're going to get out. And what you can now do, I've indicated the ones that we've got here. What you can now do, you can apply these. Now I can promise you that this image behind me is unique. I've just basically taken the 3 and I looked across the whole lot, and I looked for ones that I thought had little bits of information. So I basically pixel peeped on these, so get them big up on the screen, and I look for sort of some exciting little bits of detail. And you can take those and then you can put them together into an image like this, and you can try them with red, with green, with blue. You don't have to do 100%. You can do, what happens if I put this one 70%? What happens if I put this one 120%? You can move these around, and that's the art part of astrophysics or astrophotography. And while you will have seen this, basically the structure of this before, this one is unique to me. It may have been copied now. I mean, statistically it's quite viable, but I doubt it. But out of this, you can start to see quite a lot of interesting features. Again, the resolution on this is huge. You can see perhaps some sort of black coming up here. These are called bow shock waves. So what this is basically gas in space that has been blown by either a supernova or something similar. It could be some other type of star ejecting something that basically blows the gas out of the way. You can see some other interesting features here. And it's basically amateur astronomers that have found some of these sort of, again, more interesting features here. And if you look across this image, again, it's a huge resolution. Amateur astronomers have discovered things. Oh, what's this little star here, and why does this little, why do we have this? And they can track it back, and they can see the star, and it's quite a huge amount of data that you can go through. I'll just give you a little bit sort of a detail on this. You can take this with a reasonably good camera, but you'll get nothing like the resolution. I'll show you where this, the details of this. But again, you can see bow shock waves again of the gas being blown out by a very large force. In terms of size, just to give you an idea, these things here are going to be several light years across. So if you put the entire solar system in there, you'd see it about the same size as the laser dot there. These things are huge. So to give you an idea of this, so the moon in here would be about probably this size. So this is pretty big. Again, you can't see these with the naked eye, but they're pretty big. They're out there. The Andromeda Galaxy, which you can see with the naked eye, look it up. It's called M31. It's basically just a fuzzy blob on a very good sky. It's about 8 to 10 times larger than the moon. If you actually see it, it's pretty big. You can see that from here. So basically this little tiny area on the top here, as you can see, goes down. This area here is the area we're looking at, and this tiny little area here is this area here. So it's quite a lot of detail in that. Another absolutely critical part of the James Webb Space Telescope is the ability, because it's in infrared, and the reason that we have to use infrared is because as the universe is expanding, it's basically getting bigger and bigger. As the further away we get, the further away things are, the faster it's expanding. And as things expand, they have a redshift. Just as you hear a police car, an ambulance, a fire engine go past you, or even a car or a plane, you'll hear the noise goes down a pitch as it goes past you. The stars do the same thing. The light goes redder. That's what we call redshift. Anything that's coming towards you, it goes blue. We don't see much blue shift, fortunately, because things coming towards us, not a good sign typically. Everything is moving further away. It's all getting redshifted. Now, this redshift, with my telescope, I can see galaxies up to about 1 billion light years away. And that means that the light in those is redshifted by quite an appreciable amount. It actually takes it outside, so anything in the hydrogen alpha is no longer in hydrogen alpha. It comes out of my filter range. So anything I see is actually not what I wanted to see because it's been redshifted. But when you get right out to the edge of the universe, these things are shifted a long way. Now, remember I told you that hydrogen alpha is the most common emission line that we see. There are others, and these are, if you like, signatures of light. And as we see these lines, so here is something close by. We see these lines. Here's hydrogen, here's oxygen. As things move away, these same signatures, exactly the same, move down the spectrum. And we know it's not just like seeing a red star and going, oh, that's a red star, it must be going away fast from us, because you don't know if it's red anyway. It could be right next to us and red, or it could be right next to us and dark red. And we go, okay, well, is it moving away? Because you can't see whether it's going away from you. So we use these signatures here to basically work out, so this entire signature moves down the red spectrum into the red and infrared spectrum, so much so that as you see these things that are 13 billion light years away, right on the edge of the universe, are so redshifted, they're right off the edge of what the James Webb Space Telescope can see. Ultimately, it gets so far that they not only do they redshift, but the light gets dimmer, that you literally fall off the end, and that's as far as we can see with the observable universe. So this is a typical picture. And as they spot various different galaxies here, they see these what look like little blobs. They measure the spectra that come off these, and we see these signatures. That's how we can measure these very accurately. Now, there is a big challenge at the moment as to how we're measuring this and how old the universe is. That's all new information and new exciting things. When something goes wrong in physics, it's exciting, because it means all of your assumptions in the last 100+ years are wrong. And it means that's exciting, because it just means there's new mathematics to be sought. And at the moment, the way we measure the size of the universe, the age of the universe, and the distance of things by two incredibly accurate mechanisms differ from each other way more than the error bars should do. So one says it should be here, the other one says it should be here. The error bars don't match up. So either that process is wrong or that process is wrong, and both of them are incredibly accurate and have been backed up by decades of data. And that's really exciting, because something's wrong somewhere. But taking all that aside, this is how we measure these distances here. And as you get closer and closer to the edge, these become more and more redshifted. And that's how we're measuring the size. So that's it, folks.